Welcome to chapter 15. We are going to talk about acids and bases and their theories in this chapter. But in general, before we start anything, when we talk about acids, you may remember a sour taste like vinegar, like lemon. And when we talk about something basic, you might remember the slippery feeling. So you are right, but we're going to learn about their structures. Before anything else, let's talk about these three theories of acids and bases, and then we work on the acidic strength, and at the end of this chapter we will work on some of the calculations. So let me adjust the camera and let's start. There are three theories in acids and bases. We will learn those three. Arrhenius concept is the first thing that you know. It talks about the hydrogen ion and hydroxide ion in aqueous solutions. So, based on Arrhenius theory, an acid, an acid is a substance that releases hydrogen ion inside aqueous solution or aqueous solution. And a base is a compound that releases OH in an aqueous solution. This theory is the weakest theory of acids and bases. Why? Because we are limited to aqueous solutions. Aqueous solution means water should be the solvent. But what if our solvent is something besides water? So, according to Arrhenius theory, let's say HCl changes to H and Cl, hydrogen ion and chloride ion. So this is an acid because it releases, if we have it in the water solution, then because it releases hydrogen ion in the aqueous solution, so this is an acid. Or NaOH, which you will find in the soap. That's why soaps are slippery. Then it will release Na and OH, so it would be a base. So that's simple. This theory is simple, but it is weak because it's not going to answer all the questions about the acid and base reactions. So let's move to the second theory, which is stronger, and it is called Bronsted-Lowry. Bronsted and Lowry worked together on this concept. According to this concept, an acid is a hydrogen ion, or you call it hydronium ion, both of them. Either one. And I tell you what is the difference between hydrogen ion and hydronium ion. An acid is a hydrogen ion donor. We call hydrogen ion proton. So if you hear me keep saying proton, 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 I don't mean that particle. I mean the hydrogen which has lost an electron. Hydrogen has one electron, one proton. When it loses its electron, what is left for it? It's proton. So that's why we call it a proton ion. And this is called hydronium. So what is the difference? They technically are the same. These two, hydrogen ion or proton and hydronium ion, are the same. But what is the difference? When a substance releases hydrogen and this hydrogen sticks to water, then it will form a hydronium ion. So hydronium ion is the same proton or hydrogen ion in water. Okay, I told you technically the same, whether you say this or this, but when we're talking about the hydrogen ion in the water, we show it as hydronium ion. Okay, we talked about acid. We should talk about base in this theory. If we have a donor, we should have an acceptor on the other side, right? So hydrogen ion or hydronium acceptor. And when you pay attention, unlike the first theory, we are not limited to aqueous solutions. Did I say anything about what type of solvent? No. So you can have any type of solvent. An example from your PowerPoint slides, it's H3o positive plus NH3. So you will have H2o plus NH4. So let's check the concept of acid and base based on what we just said. I want you to compare H3o and H2o. They're similar, right? What is their difference? Can you see the difference is H3o has one more proton, has more hydrogen than H2o. So it seems like when H3o changed to H2o, it donated one proton. I hope it's clear. 3 hydrogens, 2 hydrogens. So according to this theory, this hydronium ion should be an acid because it has donated one proton to change to H2O. So we call it an acid. But if you follow the changes from NH3 to NH4 plus, what would you see? 3 hydrogens, 4 hydrogens. Seems like NH3 has accepted a proton. So according to Bronsted-Lowry concept, it's a base because it has accepted a proton. If you have an acid on the side, on one of the sides, acids are, right or left. If you have one acid, you should have one base. You cannot have 2 acids or 2 bases because if you have a donor, you should have an acceptor. Now, one more thing in this theory, it's a mutual relationship between left and right. So you see H3O has lost a hydrogen to change to H2O. But if the reaction goes back from right to left, H2O is going to attach to hydrogen, is going to accept the hydrogen to go back to H3O, right? I'm going from right to left. I'm talking about right to left. H2O to H3O. What should happen? H2O must accept a hydrogen to change to H3O. So can I say H2O on the other side acts as a base? Yes, because it should accept one proton to go back to H3O. So there is a relationship between these two. We call them conjugate acid-base pair. This is what you need to know for exam. This is what you need to be able to determine. First, determine the acids and bases on each side, and then find the conjugate acid-base pairs. We can say the same thing about NH3 and NH4. Going from NH3 to NH4, it accepts one proton, NH3. If you're going from right to left, then NH4 must donate a proton, get rid of 1 to change to NH3. So on the other side, NH4 is an acid. And then again, you have a conjugate pair. Because I don't have enough space, I just put conjugate pair. But I mean conjugate acid-base pair. So that's what you need to determine. And in general, how do we determine the conjugate acid-base pairs? If this is the base, in the general formula for the base, and if this is acid, so what do you see the difference? The difference between a conjugate acid-base pair is just one hydrogen. Acid should always have one more hydrogen to donate it. We said acid is a donor. So this hydrogen will be donated to change to its base, as you see here. Here NH3 and NH4. again, this is the general format, okay? General format. NH3 and NH4, can I say they are a conjugate acid-base pair? Yeah, we just said that. 3 hydrogens and 4 hydrogens, and the non-metal is the same. Can I say, for example, and here also you see it, H2O and H3o. Can we say they are a conjugate pair? Yes, because the non-metal is the same and there are 2 versus 3 hydrogens. Can I say HS and H2S are conjugate acid-base pair? Is the non-metal the same? Yes, both sulfur. What is the difference between the hydrogens? 1 hydrogen, 2 hydrogens. So this is another conjugate acid-base pair. How about this? The non-metal is the same, but what is the difference of the hydrogens? It's not 1, it's 2. This sulfide does not have any hydrogens, but H2S has 2 hydrogens. So because the difference is 2 hydrogens, this is not a conjugate acid-base pair. Conjugate acid-base pair, the difference is only and only 1 hydrogen, as you see in each of these examples. Learn it well for the exam. So that's all you need to know for conjugate acid-base pair. Let's work a little bit more on this before we move towards the Lewis acid-base theory. Working on slide number 17. It says, what is the conjugate acid of H2O? So when it's asking for conjugate acid, means this is a base, right? What did I just say about the difference between conjugate acid-base pairs? I said acid has 1 more proton than the base. Proton means H plus. So it's H2O plus H plus. So it is what? H3O with a positive charge because it has gained a hydrogen with a positive charge. We have what is the conjugate base of H2O? If this is our acid, what is its conjugate base? Conjugate base has 1 less hydrogen ion. So H2O minus a hydrogen ion. First of all, it has 1 hydrogen then, and you know, but you write OH as OH, not HO. And because it's minus 1 hydrogen ion, so it's OH negative. But here it was plus 1 hydrogen ion. So be careful about the charge as well. That's it. You don't have much more complicated than that. But we can work on slide number 17 also. That's a good question. Label each species as an acid or base and then identify the conjugate acid-base pairs. I will do A for you, and then as practice, you do B for yourself at home. If you have any questions, let me know. HCO3 plus HF H2CO3 plus fluoride. So let's determine which one is acid, which one is base, and then identify the conjugate acid-base pairs. So, So, what is the difference between HCO3 and H2CO3? Which one has more hydrogen? It seems like this has accepted the proton, right? So HCO3 is a base, H2CO3 is an acid, right? Because if it wants to go back, it has to donate 1 proton. So this is one of our conjugate pairs. This is what we need to understand from this theory. And then for between HF and F, seems like HF has donated a proton to change to F, to a base. And if you check, you have an acid and a base on the left side and an acid and a base on the right side, and it makes sense. We should have one acid, one base on each side, not two acids and two bases. So since this is the base, it accepts a proton to go back to HF, then here's another conjugate pair. Now we can easily work on B. Try not to look at the answer though, huh? Before we finish this theory, we need to talk about amphiprotic or amphiteric species. So, what does this word remind you of? Amphibians, right? So what are the amphibians? Those are the creatures, those are the animals that can live in two different places, right? So like the frogs. So you are dealing with the species that have dual function, like HCO3. HCO3 can lose a hydrogen, right? And change, let's say, HCO3 plus water. Can lose a hydrogen, can be an acid, and water can be a base. And color code them with the same color. With CO3, if it loses one hydrogen, positive hydrogen, and water is going to grab it if it's going to accept it, so it's H3o, right? But at the same time, this HCO3 is ready to accept a hydrogen, change to H2CO3, and water can be your acid, the donor. So HCO3 can go either way depending on the situation, the conditions. It can act both as an acid or a base. So such a substance is called amphiprotic or amphiteric. Okay, the last theory of acids and bases, the last concept is Lewis theory. This theory is completely different from what you learned, because instead of hydrogen ion or hydrogen ion and OH ion, is just talking about an electron pair. According to this theory, an acid is an electron pair, the whole pair, not just one single electron. Electron pair acceptor. Learn it. Acid, accept. In Lewis. Acid, accept. And base is an electron pair donor. Okay? Let me give you an example to understand. But before that, let me tell you how to determine the acids and bases in this theory. Acids should accept, right? So they either have a positive charge, atoms with the positive charge, or atoms with empty orbital. Which atoms are famous for empty orbital? Aluminum, gallium, boron, and gallium. Let me write them in the order. So the first three elements in group 3, in group 13, are famous for having empty orbitals. What can be a good Lewis base or electron pair donor? Atoms with negative charge, or atoms with lone, or instead of lone, let's say non-bonding electron pair. So electron donor should have a good source of electrons, and electron acceptor should have room for accepting those electrons. An example that you have on your slide number 21 is BF3 from Chem 1. You remember that boron, aluminum, gallium have empty orbitals. And that's why instead of 8, instead of octet of electrons, you just see 3 bonds or 6 electrons. So it means that it has an empty orbital already. So it's added to NH3. What do you see on top of nitrogen? Electron pair, non-bonding electron pair. So what happens? This nitrogen is going to donate the electron pair onto boron. So since BF3 is the electron pair acceptor, is the Lewis acid. And since NH3 is electron pair donor, so this is the Lewis base. Okay. Now let's see what happens. BF3. Of course, there are electrons on fluorines. I skipped drawing them, but they exist because the octet must be complete on every single atom. And then between nitrogen and boron, a new bond is going to form, and we have the new compound. That doesn't look like an acid base based on what we know, but it is the best, the most, let's say the strongest or the most rigid acid-base theory, because it can explain all the questions about acids and bases. All right. In the next video, after you work enough on these acid-base theories and their examples, I am going to work on the relative strengths of acids and bases. If you have time and if the video is not going to be too long, we will work on the calculations. If not, we will move towards the third video. Make sure you understand these acid-base theories really well, because we are going to work with them.